సార్ క్వశ్చన్స్ ప్రిపేర్ చేస్తున్నా.
All right. Good morning, everyone. Can you hear me?
Yeah, we are able to hear.
Okay. Thanks. Good morning, everybody. So today the topic is applications of energy storage system in smart grid. So yesterday we have introduced the 5 different types of energy storage technologies, which are mechanical energy storage system, electrical, all right, electrochemical, chemical, as well as the thermal. Right. So we have introduced their basic working principles and their technical specifics. And I hope you can realize that these different energy storage technologies, they have different applications. For example, for pump hydro storage, it has a very large power rating as well as a capacity. So it is more suitable for bulk energy storage. While for the supercap or for the lithium-ion battery, they have a relatively smaller um, power rating, but their responding time is much faster. So they may more suitable for power system operation and control support. So today I'm going to introduce this is outline of my lecture today. So basically, I will have a quick review of typical applications of energy storage in power system for the realistic projects ongoing. And after that, I will introduce three specific applications, which are frequency control, load leveling, as well as the UPS, uninterruptible power supply as a backup power source. And in the second section, I will give you an in-depth look at the load shifting application from the utility perspective. Actually, by shifting the loads, we can do the peak shaving, while in the meantime, we can also save power loss. So that is actually an added value of the energy storage based load shifting. So I will give you such a kind of analysis, including certain mathematical models and formulas. And last, we will have an overview of some issues in the energy storage applications, mainly safety and disposal concerns. So that is the outline of the lecture today. Now, let's take a look at some real-world energy storage facilities and their applications. So you can see here in this table, this table actually was extracted from this article. And you can find that around the whole world, from Australia to USA, Japan, Europe, Germany, and Middle America, Puerto Rico, Asia, Japan, China, Ireland, Spain. You can see that there are already many commercialized energy storage stations installed in the power grid. And look at their rating, you can see some of them are beyond 10 megawatt in terms of the power rating, and in terms of the capacity, you can see for this one is more than 240 megawatt hour, so which is very big. And some others, you can see this one. Different technologies are used, including the battery energy storage as well as a supercapacitor. So you can see this supercapacitor, two projects in China and Spain. The capacity is not that big, just in the kilowatt hour range, 17.2 and 5.6, not that big, but their power rating is quite big, 3 megawatt and 4 megawatt. So they are mainly for the dynamics support to the power grid, including the voltage sag mitigation and the frequency stability. Okay. And the flywheel, flywheel system, energy storage system are also installed. You can see the capacity for this one in Japan, more than 200 MVA, very big. And in USA, this is a 20 megawatt for frequency regulation and power quality application. Remember yesterday when we introduced flywheel energy storage, it has a relatively faster responding speed because the rotational speed of the spinning wheels are fast. So they are also useful and suitable for the fast system dynamic support. Okay, and even SMES. Okay, SMES is also like demonstrated with a 10 megawatt capacity project in Japan is also for system stability and power quality because their responding speed are faster, right? Faster than other types of the ESS. But most of the projects you can see they are using battery energy storage technology because the lithium batteries, lead acid batteries, they are already very mature and commercially viable. Okay, and in terms of the applications, if you can if you can count these keywords, you can see most of them are actually used for frequency, right? Frequency response regulation, frequency control. Some are for spinning reserve, and some for wind power fluctuation mitigation. And this one is for load leveling, okay, wind power fluctuation as well. So basically, you can see most of the energy storage system are used for frequency control and frequency support. So why frequency is so important and why energy storage can play such a role? Today, I will also introduce the working principle as well as some simulation results. Okay, so as I said, I will introduce three typical applications, including load shifting for the first place, because this one is most traditional. Then I will give you a more in-depth introduction to the frequency control using the energy storage system. And then the third application is for uninterruptible power supply as a backup power source. All right, so for load leveling, okay, I suppose everybody can intuitively understand how does it work. So basically, we want to shift the load from one period to another period, right, through charging and discharging of the energy storage system. So by doing this, we can avoid the peak power demand, and we can shift the peak to the off-peak period. So the total power curve of a day or of a certain period will be more smooth, right? So this is the purpose of the load shifting. So here is an illustration. Okay, we have two curves, blue and red. So originally, you can see this is the blue curve. This is a blue curve original load, but clearly you can see we have two peak hour. Okay, we have two peak load period. This one and this one. So if you want to smooth this power curve, and we can charge and discharge the batteries. So during this peak period, we can discharge our energy storage. So part of the load is actually supplied by the energy storage. So from the net load perspective, the net load becomes this red curve. Okay, becomes this red curve. And then during this period, because we have to restore the energy storage, the state of charge. So during this off-peak period, we will charge our battery, right? We will charge our battery, restore the energy in the battery. So you can see here, we will charge the battery during this period. Then the net load curve remains this red, one. And for the second peak period, we do the same, right? During this period, we will charge our battery, and after that, during the peak period, we will discharge our battery. So the net total power demand becomes much smooth, right? And very importantly, you can see the net power consumption of the whole system becomes lower. That by doing this, the power utility companies, they do not need to expand their power infrastructure to satisfy such peak load. What they need is just to satisfy this red peak net demand. So they can save significantly the total investment cost. So for this type of the load shifting, you can see since we need to charge and discharge the power at a high power rating as well as for a certain long duration time. So importantly, this type of energy storage should have a relatively higher capacity. Okay, should have a relatively higher capacity. So sometimes we may use the pump hydro, right, which has a biggest energy capacity. Then if we have compressed air, CAES, we can also use that. But if we have other large-scale energy storage stations, such as the one listed here, when they are over 10 or even 100 megawatt hour, they may also be useful in this case. Okay. Now, so the first benefit is very clear, as I mentioned. By shifting the load through charging and discharging, we can smooth the load curve. Okay, we can avoid the peak. We can fill the valley and off-peak load demand. And besides, it can actually provide some additional benefits. So this one I will introduce in the second part of the lecture this morning. Okay. Then next, I think this is a major focus of the lecture today for frequency control. Okay, frequency control based on energy storage system. So before we start, let's have a recap of the frequency. Okay, everybody, I suppose, knows how does a frequency mean, right? In our power grid, we have 50 hertz AC electricity supply. But generally speaking, this frequency is a reflection of the rotational speed of the synchronous generator, okay, of the synchronous generator. And practically, this frequency depends on the balance between the power supply and the power demand. Okay, so if the supply is larger than the demand, the frequency will grow, right, will increase. And reversely, if the demand is larger than the supply, the frequency will decrease. So the frequency really depends whether the supply and the demand can be real-time balanced, okay? And clearly, the frequency is one of the most important parameter for system stability, because our appliances, our electric motors, all kinds of loads, they are designed to operate near 50 hertz, okay, near the standard frequency value. And besides, especially for some high accuracy engineering, let's say semiconductor manufacturing, we have to maintain a very high standard of frequency. Otherwise, it will cause the malfunction of the production line. So that is a very important criteria for power quality from the consumer's perspective. Now, in this table, I'm showing the frequency standard as well as the tolerance. Okay, very importantly, you should understand. Theoretically speaking, the frequency, the power supply and demand cannot be exactly balanced, because from second to second, minute to minute, every instantaneous moment, the load will be changing, right? Just for me, for example, if I turn on the light, I will decrease the load, right? If I turn I turn off the light, I will decrease the total load of the system. And then if I turn on the light, I will increase the load. So every time, every second, numerous customers, they are using different power demand. So the power demand is always fluctuating. So the power supply should catch up with the load demand fluctuation, right? If this balance is temporarily broken, as I just mentioned, the frequency will fluctuate, will deviate. But actually, we have some tolerance range for the frequency to fluctuate. For example, in Singapore, for normal operating conditions, we can allow plus minus 0.2 hertz frequency deviation. Then in Europe, the same. In Australia, it's more stringent. For interconnected system, they can only allow plus minus 0.15. But for islanded system, they are quite generous, 0.5 hertz plus minus. Okay, so that is for normal operation. Just what, as I said, okay, if we just randomly turn on and off our power supply, then we can, power demand, then we can tolerate such a frequency. However, in reality, sometimes the big disturbance may happen. For example, the outage of a generator caused by, let's say, short circuit, or caused by operator's malfunction, or even caused by a rainstorm or even earthquake, right? That may happen from time to time. So under this emergency scenario, then the frequency will dramatically decrease, as I show here in this figure. So you can see that originally the frequency stays at the steady normal state, 50 hertz. Then we have allowable tolerant range, right? Suddenly there is a big disturbance, for example, outage of a generator. Then the frequency will dramatically, rapidly decrease until a lowest point, which is called frequency nadir. And this change of the, rate of change of the frequency is called Rakoff. Remember yesterday when we introduced PMU, and PMU can measure this Rakoff. And I remember one student asked, how can we calculate this? You can see this Rakoff is easy to calculate. It's just equals to df over dt, right? We just calculate df and divide it by the dt. Now, so for this initial period, how fast the frequency will decline and how low the frequency will decline depends on the system's inertia response. Okay, because the generators, they have inertia. They are rotational machines, so they have inertia. After the balance is broken, the kinetic energy in the rotor will release. So it will gradually, decline the frequency and until the lowest point, nadir. Then after that, the frequency will be gradually recovered by the system control systems, including the primary control system and then secondary control system. Okay, these two control systems will gradually recover the frequency. And importantly, you should know primary control is faster. Okay, it immediately acts within several seconds, and it aims to instantaneously, restore, mitigate the frequency deviation, a frequency decline. And after that, the secondary control system is relatively slower. However, it aims to fully recover the frequency back to the normal. Okay, back to the normal. And here, I have also listed the tertiary control. Tertiary control is mainly for economic dispatch. Okay, especially for economic dispatch. So under this emergency scenario or condition, you can see different countries, they have different security limit or constraint. In Singapore, as long as the frequency drops below 49.7, we have to shed the load. This is the criteria. Okay, and Europe, the frequency deviation, the nadir point is plus minus 0.8. But sometimes the frequency may increase if there is a sudden outage of the load substation. Okay, then the supply becomes excessive, so frequency will also increase and violate the upper bound. That is why you put the plus minus 0.8 frequency. Then Australia, you can see plus minus 1. Okay, and the tolerance is 47 to 52. Okay, so Australia has a relatively more stringent requirement for the frequency performance during the emergency conditions. So that is some, basic concept and the basic requirement for the frequency. Now, here, what I'm showing is a frequency control block diagram coded in MATLAB Simulink. I suppose everybody, if you are familiar with this control block diagram and the Simulink, you can quickly do a model in the Simulink, right? So let me briefly introduce how does this mean. So generally speaking, this control block diagram has several blocks, and this block is corresponding to system inertia and the damping coefficient. Okay, so you can see we use H to denote the system inertia. That is a kind of physical property of the rotor, of the synchronous machine's rotor. And D is the damping from the load side, because for some load, when the frequency decreases, the power consumption will also decrease. That is a so-called damping effect of the load. I suppose some students, if you have learned, power system control, this is a very fundamental concept. And this is to describe this part. This block is to model system and the load. And how about the generator? Okay, generator are modeled here. Let's say if we have many generator 1, generator 2, and generator N. Each generator has a governor and a turbine being modeled. Now here we use TG and TT to denote their time constant. But clearly, S is S domain, okay, in this control block diagram model. So that is for the generator. Now the power demand, okay, power demand come from the PL. Delta PL means the change of the power load, okay. So if the power demand is changed, then the frequency will change as well, right? The frequency will change as well. That means you give a delta L as an input. After this block diagram, you will see a delta F. So the frequency will deviate. Now, as I said, we have like two control systems, primary control and secondary control. So you can see, given this delta F, this primary control block will immediately react to this delta F. Okay, so here you can see the control unit is 1 over R. R is the so-called regulation coefficient, okay, or Joule coefficient. Now, given this delta F, then given this R, for different generators, each generator will have such a primary controller. Then it will generate a signal. Okay, this signal will change the location and the position of the governor, and then it will allow more or less gas input or the energy input, so as to restore the frequency a bit. So that is a so-called primary frequency control block. Okay, this denoted in these blocks. Okay, now you can see that this primary control is just based on this simple proportional control unit, right? 1 over R. So if you are familiar with the control theory, the proportional control cannot eliminate the control area, right? The delta F, the control area, given this 1 over R, it cannot eliminate delta F. So my point is, even after this primary control block, the delta F remains not non-zero. There will be still a delta F. But our objective is to restore the frequency back to 50. So we have to eliminate the delta F. So how can we do? Then we will have a secondary control block diagram, control block unit here. Now here you can see that this secondary control block is based on the PI controller, so-called proportional integral controller. You can see we have two units. One is proportional, another one is integral. Now, this proportional integral controller is able to eliminate the frequency area, delta F. It will eliminate the frequency delta F. So you can see the delta F, first of all, they will go through this B. B is also a coefficient. Then if this system is connected with the neighboring system, then there will be a tie line connection. So we'll also take this tie line power change as an input as well. Now they will form up the signal called ACE, area control area. Okay, this ACE will be inputted to this PI controller, and after that, this controller will issue the control signal for different generators. And in terms of alpha 1 to alpha 2 until alpha n. Now each alpha will combine with the primary control signal together and then go to this generator. Then this generator, after receiving these two control signals, they will adjust their speed of the so-called governor speed, and they will also adjust the input of either the primary energy resource, let's say the gas input to the turbine, or for the hydro generator, the water flow input to the hydro turbine. So in the end, the frequency will be fully restored. Okay, so that is generally how the frequency is controlled in the power system. Now, question is, challenge is nowadays we have more wind and solar power, right? As I introduced in the first day. And besides, we may also have HVDC links for large-scale power interconnection. And for the load, we have more and more inverter-based loads, such as data centers. Now, unfortunately, the wind and the solar power, they are also installed. They do not have inertia, right? Wind and power, we have already explained, they are interfaced through converters, so they do not contribute edge. And the load, the inverter-based load, they do not have damping either. So you can see that when we have more power converter interface generation, and when we have more inverter-based load, both H and D will decrease. Okay, so the system total inertia and damping will decrease. And the system is more sensitive, more vulnerable to power disturbance. In other words, if you give the same power disturbance, the low inertia system will see a larger frequency deviation. Okay, and besides the HVDC, they will separate the system into as non-synchronous portions, so they cannot support the frequency to each other. That is an issue. Okay, and another issue also comes from the renewable and the renewable generation and the low demand. For the renewables, the wind and the solar power, they are highly intermittent. So they will input more frequency disturbance, power disturbance, as I shown here, delta PV, delta wind. Okay, you can see from time to time, the power balance between the supply and the demand are broken. Okay, and besides the load, right? The load, we have demand response, we have EV charging load. They are also stochastic and random. So they will also inject more power disturbances. Now you can see that under this situation, right? We have less inertia, we have less damping, but we have higher power disturbances. So you can imagine the frequency of the system is becoming more challenging, right? More challenging. Now the question is, how can we manage this? How can we support the frequency in such a context? So we need to have new resources. We need to have new frequency regulation resources, and we also need to have new methods, control methods. Okay, control methods and sources. So what will be these frequency regulation sources? Okay, since the topic is energy storage today, so certainly energy storage could be a useful source for frequency regulation. Okay, so here let me show once again this control block diagram. So basic idea is we can incorporate the energy storage system into the control block diagram. And this energy storage can either provide primary control or the secondary control to the system. Okay, the original part is the same, but we have a new source. Then this energy storage can, replace the traditional generator to catch up the, frequency deviation. Now, practically, this free energy storage, they can be in the form of large-scale power grid energy storage station in megawatt-hour level, okay? Or they could be small-scale energy storage units spread in the power grid, and they can be aggregated together to provide total charging discharging support to the system. So both of them are realistic in reality. So in our research group, we have research on both. This paper introduced a method to aggregate the small-scale ESS unit to provide frequency control. And this paper develops a method, AI-based method, to control large-scale grid energy storage station to provide frequency support. So that is some realistic works. Then the key challenge is, okay, number one, when we want to use energy storage to support the frequency, what will be the required size? Okay, so theoretically speaking, the larger size of the ESS can give you a better frequency support. But the question is, the larger size of ESS need more investment. It's more costly. Okay, so we need to determine the optimal size of the ESS. That is something to optimize. And after we decide the energy storage system size and its location, we need to design the control system for the ESS. We need to optimally charge and discharge it to regulate the frequency. Okay, that's it. What we have proposed in these two papers. So if you're interested, you can take a look. Now, let me quickly show some simulation results using ESS to regulate or support the frequency. So here you can see this upper window shows the solar PV power output of a day. The data come from Singapore. You can see from 8 a.m. early morning, there will be a gradual increase of solar power. However, it's always highly fluctuating, right? because of the, because of the cloud movement, cloud coverage. Okay. Now, if we just look into this we have a 24 hours, right? If we just look into this 1 hour solar power output, you can see within this 1 hour, the solar PV also fluctuates significantly, right? Especially during these minutes, you can see it suddenly becomes full and then drop to 1/5, then restore to 250 again, then fluctuate significantly. So if this PV, fluctuates like this, the frequency will, fluctuate as well, okay, as well. So here we want to use the frequency, we want to use the energy storage system to regulate the frequency fluctuation. Now here, let me show the corresponding frequency of the system fluctuation due to the energy storage, due to the solar power output. You can see here in the bottom window, this is original frequency of the 1 hour. You can see the frequency also fluctuate significantly, especially during this period, because this period you can see we have a large solar power fluctuation. Now you can see the highest and the lowest frequency is around minus 0.7131 to 0.117. Okay. Now this is the original case without ESS. Now, if we add the energy storage system to the grid and control it in this way, you can see we have much smoother frequency deviation, right? So here you can see the maximum and minimum bound become almost half of the base case. And if you look at the frequency fluctuation, it's also much small. Okay, so you can see ESS can significantly regulate the frequency fluctuation. Right. Now, the next question, as I just mentioned, we need to decide the right size of the energy storage. Intuitively speaking, a larger energy storage system will give you a better frequency performance. However, we need to consider the cost as well. So here we are comparing the frequency performance for different sizes of the ESS. Now we compare 50 megawatt hour, 100 megawatt hour, 200 megawatt hour capacity of the energy storage system. You can see that clearly, right? When the size increases, the frequency, including the maximum deviation as well as the fluctuation magnitude, is continuously decreasing. However, we need to consider a balance between the total cost and the total effectiveness. So we have to do the so-called cost effectiveness analysis. Okay, so practically we can go through different sizes of the ESS, and then we simulate the corresponding frequency performance. Then certainly there will be a kind of a balance between the two, right? We can just calculate the total capacity divided by the total performance index. Then we can have such a sensitivity. And the optimal size should be the one with the marginal sensitivity value. Okay, which means when we further increase the ESS, the frequency performance improvement will become marginal. So that is the basic idea for selecting or optimizing the energy storage system size. Okay, so that is the first application for energy storage system, which is most widely applied in real world. Okay. Then the next, the third one is the actually the second one. Okay, sorry, this is the second one. The second one is the uninterruptible power supply, UPS, and this one is also a typical application of the energy storage system in our power grid, because from time to time, the power grid may experience disturbance, and if the disturbance is too severe, it may lead to blackout. Right. So for very critical loads, for example, data centers, hospitals, government offices, we need to make sure their power supply is continuous and uninterruptible. So we have to place some backup power sources. And this power backup sources could be small diesel generators, or they could be energy storage systems. Okay, for diesel generators, they are starting up speed may be slow, but energy storage system, you can see, is very fast. So most of the case, we will use the UPS as a power supply. Okay, now most of the time, if you look at the commercial products, the UPS are based on using lead acid batteries, because the lead acid batteries relatively they are cheaper, and they are more mature, and so this is the lead acid batteries. And besides, there are also commercial solutions using compressed air, okay, small scale compressed air, or even large scale compressed air storage to provide the power supply under emergency conditions. And besides, another offer is based on flywheel. Okay, flywheel certainly has a faster responding speed, but once again, flywheel is more expensive. So here, this is an illustration of the power UPS. So here you can see it is a combined UPS with a battery with a diesel generator. Okay, so this is a power grid power supply, and this is our critical load. If there is a power, outage from the grid or from the power supply source, then generator will immediately, you can see, take over the power supply. So that is, a quick illustration. Now look at some practical power supply products that you can see here. These are lead acid batteries, because they are more mature, they are cheaper, right? This is for large scale data center, and for small computers, we can also have a backup power supply. We can also have this UPS for small computers. Okay, small computers. This is the third. Yeah, the second application is frequency control. So the third is UPS. I was wrong. All right. So in terms of the UPS design, we need to consider several criteria. Number one is the switch over time. Okay, switch over time. So let me quickly show this UPS based on the battery. So now you have this power load. This is your power grid. You can see under normal conditions, the grid is supplying the power to the load. And in the meantime, the grid is charging the battery. Okay, this is our UPS. And the battery is connected with the inverter. Okay, because this power demand may be an AC demand. So we need to have a DC-AC inverter here. So this is a normal condition. And suddenly, if there is an outage, or if there is a kind of power quality issue happened in the manpower supply, right? Immediately the battery and the inverter should switch on and take over the power supply to the load. So this whole process should be very fast. Otherwise, the load will still experience certain blackout time. Okay, especially for data centers, for a semiconductor manufacturing, for high accuracy equipment, we have to make sure this switching time to be short. Okay, so you can see that the commercial products, they can achieve 25 milliseconds. Okay, 25 milliseconds, they can take over the power supply. So we have to use such high responding power source and inverter, okay, to design this UPS. And another criteria is about the capacity, is about the size of the UPS. Okay, so in reality, the UPS batteries, they are in the modular format. So for example, one UPS battery is 6 kVA. Okay, now depending on our load, sometimes we will use so-called N+N+1 criteria in order to address the so-called single point failure. What does that mean? Okay, if we have 12 kVA load and each UPS module is 6. So sometimes exactly we only need two modules, right? 2 times 6 equals to 12. But in order to consider the single point failure, for example, there might be possibility that the UPS module will also, fail. There may also be like outage. So in order to consider this single point failure, we need to add one more reserve. Okay, we need to add one more redundancy. So it's called N minus 1. 1 means the additional modules as a redundancy. So that even during this UPS power supply condition, if one module is out, we can still supply the full load. Okay, so that is some design criteria for the UPS power supply. Okay, so that is three, typical applications for the energy storage system application. Then in the second part, I would like to give you an in-depth look at the additional benefit from the load shifting from the utilities perspective. Okay. Before that, let's have a 5 minutes break. Okay, 5 minutes break. Please come back after 5 minutes. Okay.
Okay, Professor.
All right, let's go back. So in the second part, I will give you an in-depth analysis of the additional benefits of the load leveling through, energy storage, charging and discharging. Why do we want to identify additional benefits? Because the energy storage system, especially for the large scale station, remains very expensive. So when the power grid invest in this asset, they want to, maximize the total benefit. Right? In addition to the first benefit is already analyzed. We can shift the load from peak to the off-peak period, so we can defer the grid investment, right, on the facilities. But there must be some additional economic benefits. So one of the benefit is actually to reduce the transmission and distribution power loss. Okay, and another one is actually to regulate the bus voltage at the distribution network. But this one I will not cover it in this class. We will only focus on the power loss reduction by, charging and discharging the batteries. Okay, so wait a second. Okay, so let's take a look at the power loss. The power loss makes a big part, significant part in the total energy loss of the whole power system. So clearly, you can see that since our transmission and the distribution cables and transmission lines, they are made of conductors, right? Conductors certainly have resistance. So when the current goes through the resistance, it will generate joule heat. That will be part of the loss. So according to this paper, you can see the ratio of the transmission and distribution loss during the peak load is very big. Our transmission network it is around 2.5 to 5%. Sub-transmission network 1 to 2.5, and distribution network is even higher because the voltage is low. Right, voltage is lower, so current is higher. It is around 6 to 8%. So you can imagine that the total power loss is very big for the whole grid, and it corresponds to real money loss. So if we are able to bring down this power loss, we can save real money, right? We can save real money. So actually, the large-scale energy storage can also can also help to reduce the power loss. Let's take the analysis. Now, the power loss is proportional to the current flowing through the circuit as well as the resistance. Okay, so our purpose is actually when using the ESS to shift the load from peak period to off-peak period. We are actually changing the current. We are actually changing the current. Now, if we work on this formula, then the total power reduction can be achieved. Later, I will introduce this. But before that, we need to understand, in addition to the current, the resistance of the transmission and distribution wires and transformers, they are actually also variable. They are also variable. They actually depends on the temperature. It depends on the temperature of the external ambient temperature. So this resistance is lower at off-peak period and relatively higher at the peak period. Okay, peak period, because the frequency, the temperature is high. Okay, and also we also need to consider the price. Although we are aiming to save the power loss, but the power has different prices at a different period. Okay, especially in the electricity market condition. So our target, our principle is that you can see here, if we have a power curve in this way, I just show a kind of sine wave form to represent the load. This is the off-peak period, and this is the peak period. Okay. Now our objective is to shift the load during this peak period to the off-peak period, and correspondingly, you can see this is the power loss. Okay, the x-axis is the load current, the I, the y-axis is the power loss, I squared times R. So clearly you can see this curve is a quadratic curve, okay, quadratic curve. So you can see that when the current is higher, the power loss will increase quadratically rather than linearly, right? So the principle is that if we're able to reduce the load during the high current period, the peak period, and we shift this load to the low off-peak period, the low current period, then we will see a gap between the loss corresponding to the period. Okay, and this loss, directly speaking, equals to I square R minus I square peak R minus I square off peak R. So you can see that by doing that, although the x-axis of the current are the same, the y-axis are different. There is a gap because this is a quadratic curve. I hope you can understand my point. Okay, now, so this is a general working principle, but we do need to consider other parameters, including the efficiency of the energy storage, because when the energy storage charge and discharge, it will lose energy by itself, right? Like yesterday, we have also introduced the energy storage efficiency for different technologies. The batteries, lithium battery, they may have 95% efficiency, but others may be not that good, especially, let's say, the compressed air, ESS, okay? And we also need to consider the ratio between the peak period and the off-peak period. In other words, we need to, as long as the gap, between off-peak period load and off-peak period are big, we can save more energy loss. Okay, we can save more energy. If the load is too smooth, then there is no point to shift, right? I hope you can understand. And besides, we can also consider the variation of the resistance, okay, of the conductors, of the wires. The resistance also will be considered. So that means we have a mathematical model to analyze, okay? If we just simply model this circuit as a resistance and reactance, now clearly the total power loss, we only consider the real power loss. Only real power loss equals to, we can divide it into two parts. Right? One is the peak current period. This P denotes the peak period. And another part is the off-peak period. This denoted as this subscript O. Okay, so the total power loss is the summation of the two portions. Okay, IP squared times IP times TP. Okay, this TP is the duration time of the peak period. And this is the off-peak period. Okay, so now our principle is we have an energy storage battery, then we will charge the battery during the off-peak and discharge the battery during the peak. Okay, so that you can see during the peak period, our energy storage will discharge, so we will reduce the net power demand during the peak period. And in the meantime, we have to restore, we have to shift this load back to the off-peak period. So during this period, we will charge the battery. So you can see that as long this part of energy loss is reduced because we have minus IS, while this part energy loss is increased because we have added this IS. So as long as the reduced part is larger than the increased part, we can achieve the energy saving, right? We can achieve the energy loss saving. So that is a basic principle, and clearly you can see that this magnitude of this item and that item depends on IP over IO, depending on the resistance RP and RO, as well as depends on the period TP and TO. And note that IS is the same. So we do not reduce the net, we will not reduce the total load demand, but we shift the load. Okay, we shift the load. So according to this formula, we can analyze how these different parameters will affect the total energy loss reduction. Okay, now here let me show you the result. Okay, so first of all, as I mentioned, clearly the these two items, they depends on IP, IO, and the resistance and the time duration. Okay, the time as well as energy storage efficiency. Now, first of all, let's take an overall look at these simulation results. Okay, the x-axis is the energy storage size over the peak load. Okay, the y-axis is the drop in the energy loss over the peak load. So you can see that clearly. Initially, when we do not have energy storage for load shifting, there is no energy loss drop. Okay, when we deploy the energy storage, when we have increased its capacity, gradually you will see more energy loss decline. Okay, energy loss decline. Okay, especially for these solid curves. Okay, but importantly, when you can observe that when the energy storage size is beyond a certain limit, the total drop start to decline, especially for this curve. Okay, and for this curve, the same. You can see the maximum point happens here, and this is the maximum value. This is for this blue dashed line. This is for the blue solid line. Okay, this is the peak point, peak value for the energy loss reduction. In other words, this is the best size, optimal size of the energy storage. Okay, this is the first observation you can, observe, right? The saving in TND loss increase with the storage size up to a maximum value, beyond which the loss will increase again. Why? Because if we have too big energy storage, then we may charge and discharge unnecessary power. And this actually will increase the loss instead. Okay. So this is the first observation. Another observation is, okay, if we compare the energy storage efficiency, the solid line represents the 100% efficiency, assuming that there is no power loss. Okay, and the dashed line denotes 75% energy storage efficiency. But clearly, if we consider the energy storage efficiency, the total energy loss drop is declined, right? So you can see for the same energy storage, this blue curve in solid line and dashed line, there is a gap. There is a gap. Okay, so we have to consider the energy storage efficiency as well. And another observation is the savings in this TND loss is sensitive to the ratio between the off-peak to peak period. Okay, so why this is the case? Once again, if you go back to the formula, you can see that this total value of the two items depends on TP and TO, right? If TP is larger than TO significantly, then we can achieve higher the power loss reduction. So here you can see that these two different colors, these two different colors. This one is the off ratio between the off-peak to peak load. They are denoted in blue. And another case is the off-peak versus peak is 50%. In other words, the blue curves corresponds to kind of equally peak and off-peak load duration time. And this one, okay, off-peak over peak is 30%. That means peak load is longer than the off-peak. So for the upper two curves, they can achieve more power loss reduction compared with the lower one, the red one, right? Because for the blue curves, the case is we have longer TP. And for the red curve, we have a lower, TP. TP and TO are the same for the lower case. Okay, for the lower case. So you can see that in order to, achieve more energy loss reduction by energy storage, charging and discharging, we have to consider multiple. We have to consider multiple factors. Okay, the peak period versus off-peak period, the energy efficiency of the efficiency of the energy storage, as well as the resistance. But the resistance here is not considered because if the temperature does not change much, between peak period and off-peak period, the resistance does not make a big impact on the result. Okay, so the result, I mean, the analysis and the more detailed results are actually published in this paper, and this paper is, I mean, a very classic paper back to maybe 10 years ago. So you can also take a look if you are interested in this work. Okay. Okay, so that is the, I mean, the in-depth analysis of the additional benefit from the energy storage system based load leveling in the power grid. Okay, simply speaking, we can achieve energy loss reduction during the power transmission and the distribution. Okay. All right, so energy storage system can provide so many benefits to the power grid, to the power customers. We have introduced the frequency control. We can improve the frequency stability of the grid, and for uninterrupted power supply, we can enhance the reliability of the customer. Right, so they are all kind of beneficial aspects. However, there must be some issues. As I said, every coin has two sides. So when we have upside, we certainly have downside. Because in reality, nowadays, most of the, I mean, small scale or large scale energy storage systems are using lithium-ion batteries. As I mentioned yesterday, the lithium-ion batteries, they are very mature nowadays. And so they have been widely applied. However, there are some safety and reliability concerns. Okay, especially for the lithium-ion batteries. You know, the materials are flammable, so once they are, I mean, exposed to, let's say, car accidents or some other extreme situation, the lithium-ion battery may explode and may even catch fire. Okay, may even catch fire. So I suppose you have already seen many electrical vehicle accidents on the road, which kind of lead to a very big fire and explosion. Okay, so this is very dangerous. So that's why the manufacturers of the lithium-ion batteries, they are more and more focusing on the safety. Okay, they want to make sure that even under some emergency situations, they do not explode or they do not catch fire. So as far as I know, many advanced battery manufacturers, they have already advanced this part significantly. Okay, so in terms of the electric vehicles, some alternative energy storage system, especially the flywheel. Okay, flywheel batteries has also been demonstrated. So I mean, in the future, I will see the safety will be significantly improved. Okay, significantly improved. So this is a kind of news regarding the Tesla's. Let me just open it. Regarding Tesla's mega power energy storage station happened in Australia. Okay, you can see that there is a big fire happened in South Australia several years back. Yeah, so probably we can take a quick watch of this video. Yeah, in South Australia, okay, Tesla has placed a big energy storage station. Back to several years ago, this energy storage station has been providing frequency control support to the system. You can take a look here. This is a realistic project. Okay, so that is some, general introduction to this energy storage station. However, unfortunately, you see, they have seen a significant fire accident back to 2021. Okay, so that is a really kind of a big concern. Okay, big concern. Um, another issue, potential issue, a realistic issue, is the impact of the on the ecological environment. Because when the batteries are retired, we have to dispose the materials. But clearly, the batteries, lead acid, lithium, the electrolytes, the anode, cathode, the material, some of them are toxic. Okay, some of them are certainly bad for the environment. So one question is, how can we dispose these materials? Nowadays, many researchers and companies, they are actually doing the recycling of the materials. So number one, they want to, properly depose these toxic materials, and number two, they want to reuse it. They want to reuse it for as either secondary, second-hand, second use batteries, or they can make use of these materials to produce new batteries. Okay, so as far as I know, a lot of companies are already doing this business. So in my university, I have a colleague who is very well known in this area. They are doing the lithium battery recycling. So I have visited his lab. There is a very advanced equipment, and they can, disaggregate the battery into different segments, components, and then it extract these different materials, and then put these different materials separately to different container. And after some chemical processing, these chemicals become either non-toxic or becomes reusable. Okay, because reusable. So I think in order to address this issue, we do need more international standards, and certainly we need to have the support from the either manufacturer as well as the user. Because for the user part, every day we have our kind of small scale, small battery cells. Sometimes after it is exhausted, we just deposit it randomly. That is not environmentally at all. So from the customer perspective, we should have separate these, batteries properly. Okay, and from the manufacturer, one big question is, when the battery is to be retired, we need to evaluate whether there is a value to reuse this battery. Okay, so we need to evaluate the remaining useful life of the battery. You may probably remember yesterday when I introduced lithium battery. During the charging and discharging, right, the capacity will fade, will degrade. But once the capacity is below 80%, we consider the battery is dead. But even the battery's capacity is 80%, there may still be some kind of capacity to use, right? Although the performance for that old battery is no longer good enough, but we can still, use it for certain application. So the second use battery is also a very hot topic. Many researchers and many companies, they are investing on that. The basic idea is that number one, we have to accurately evaluate how much capacity is left for the battery. Okay, and the number two, well, we have to make sure that the reliability of this battery are still good enough, because even the battery has let's say 75% of the capacity, its reliability could be very bad. Okay, it may not perform the a proper charging and discharging at a given kind of power rating. So for this type of the poor performance uh, batteries, old batteries, we should properly handle them. Then one idea is that we may combine new batteries and second use battery together to make a hybrid system. And then we can design proper, let's say, power sharing and some other control schemes. So that is some, high level insight for this battery disposal, reuse, and recycling. Okay. All right, I think this is the end of the lecture slides today. I understand today we have seen many mathematical models here for the load leveling, and we have also introduced the control block diagram of the energy storage system-based frequency control. So I suppose our participants may have some questions. So I want to leave, let's say, 10 to 15 minutes for Q&A. Okay. So if you have any questions, please feel free to type in or ask. Okay. Any questions, please?
You can unmute, you can put in chat box.
So good morning, Anju sir. Good morning.
Yes.
Yes, sir. Sir, you were discussing about this low inertia, especially in frequency control slide. What you have mentioned here.
You wait a second. Let me take my earphone. I could not hear clearly.
Am I audible to you, sir? Am I audible to you?
Can you say it again? Sorry.
Sir, what is the impact of these energy storage systems on inertia of the system?
Okay, inertia. Okay, energy storage system. Actually, you can see the working principle is to charge and discharge during the given the frequency deviation. Okay, given the frequency deviation. So you can either control the system, control the energy storage to use this frequency deviation signal, or you can directly emulate the energy storage as a virtual synchronous machine, VSG. And VSG, it can provide inertia. So in other words, this inertia can be realized in the control manner. That is my understanding. Can you suggest a paper in which optimal design could play any challenges? Okay, certainly I can suggest some papers. In fact, our own let me share one paper, very highly cited paper of our former colleague. Quickly show here. I think this paper is a good. Okay, so this is a good paper. You can see that sizing of energy storage for microgrids. This paper has been cited by many times. I think you can see 700 times. So this is a highly cited paper. You can certainly refer to it. And I will also share my own papers in this topic. Give me 1 second. We are also doing the the planning of the energy storage systems. So we have this paper to share. Okay. Now this paper, this you can see here. This is also a highly cited paper. Optimal deployment of heterogeneous energy storage system in multi-energy microgrid. For this paper, we actually consider both electric energy storage and the thermal energy storage. Okay, so this one is also a good reference for you if you are interested. Okay, let me see any other questions. Okay, which software is used for simulating ESS? Okay, if you are doing the frequency control, you can just simply use Simulink. Okay, we can just use Simulink. This one is, programmed in Simulink for frequency control. If you are doing the optimization, you can, use either MATLAB for programming, because essentially it's an optimization problem, right? You can also use Python as well to do the optimization programming. But for dynamic simulation, the Simulink is okay. We are also using PSSE. PSSE can also be useful. A factor influence the capacity of the for frequency control. Okay, so essentially, the larger size of the ESS can give you better frequency support, but we have to consider the cost. Okay, there must be a balance between the investment cost and the frequency control effectiveness. So we need to look at this cost effectiveness. A simple idea is that we can calculate the sensitivity. Let's say the delta cost over delta effective. So we select the highest value of this sensitivity to determine the size. Okay. Can we directly connect the ESS in DC microgrid? Yes, certainly you can. Certainly you can. If you are analyzing a DC microgrid, then you need to make sure the energy storage can directly interface with the DC microgrid at the same voltage level. So I suppose that the ESS still need a converter, right? Because the ESS charging discharging is controlled by this converter. So you have to, in this case, DC microgrid, you may use a DC-DC converter. Okay, DC-DC converter. DC-DC converter is needed. Okay. Can we use measure as? Yes, in Simulink certainly everything can be well measured, monitored. Yes, Simulink can do, and the SimScape. Yesterday I suggest the SimScape. That is more. I think it's a more professional package. SimScape. This one, this MATLAB SimScape, it can, has a lot of functions to do battery SOC, battery monitoring. Yeah, you can do this one. All right, any other questions?
Professor, I have one question.
Yes,
Professor,
please.
I'm audible?
Yes, please.
Yeah, the grid inertia is very high. In that case, the energy storage system is really going to impact the frequency of a grid.
You mean the grid inertia?
Yeah.
Yeah, the grid inertia, because when we, replace the traditional synchronous machines with the renewable energy sources, we will reduce the inertia in the meantime. Yeah, so that's why the energy storage system sometimes it can be controlled as a virtual inertia generator, VSG. Okay. And other, let's say the wind power, they can also be controlled in the VSG mode. That's why VSG virtual inertia is a very hot topic in recent years. Okay. Any other questions? And in the afternoon, I will introduce the distributed generation. Okay, one more question is coming. Many research are DC in nature. Okay, this is a good question. Whether DC microgrid is better than AC, that really depends. Depends on how much DC load are there. Because although the sources are DC, however, our loads are AC. So you have any way to place a DC to AC converter. So if most of our loads are DC, then we can directly interface the DC source with the DC load. So that is certainly possible. So it's not a kind of a straightforward yes or no question. That really depends. Depends on, I mean, the number of the DC load, number of the DC source, as well as the number of AC loads. But I can tell you that a DC microgrid is much easier to control, right? Because we only need to control the voltage. There is no frequency stuff. Okay, so in our research lab, we actually have a hybrid AC-DC platform. So we have AC feeder, we have DC feeder, and in the middle there is a bidirectional converter. Okay, then DC sources are connected to DC, AC sources are connected to AC. Then by coordinating two sides, two feeders through the coordinated control of the bidirectional converter, we can, certainly improve the overall efficiency. Yes. Okay, then I think later on today, half an hour later, Professor Kumar and Vanip Kumar will give you a disk-based controller and OpenRT application to control power converters. Okay, this is also very useful, very practical. Okay, for experimental testing and for validation purposes. Yeah, so then this afternoon I will introduce a distributed generation, followed by experimental demonstration of power converter control in this space. Okay.
Thank you, Professor.
Okay, if no more question, we can finish now.
Professor,
I will.
will you
Yes.
stop sharing the screen?
Okay, I will.
No, I have to take the picture of the attendees also that need to be
Okay.
submitted. Then thank you all, and we'll start the next lecture at 10:30 by Dr. T. Vinay Kumar. Thank you, Professor.
Okay, thank you. Bye bye. See you later afternoon. Bye bye.